That's awesome. Okay, sweet. Hello. So to kind of refresh what we did last time, we are going to look at these examples, and I'm going to save like this and this to do at the exam review, so we're not seeing the same thing 100 times, but it's essentially the same type of reaction where the double bond attacks, double bond attacks. But what I do want to do with you is this example. So we know what 1,3-butadiene looks like, and we're reacting it with HCl. And here I couldn't get it to like make the double bonds like Dr. West will have it in your exam, but essentially it's going to look something like this on your exam. CH2, C, C, H, CH2. Hold on. I just want to make it look as much like what it'll be on your exam as possible. So that's A. You guys, you get the point. CH3, I've already started, so I'm just going to go ahead and finish. All right, so while I'm drawing this last one out, which one do you think is going to not be a possible reaction? And then someone said they missed the first part. So all I was saying is we were reviewing the reactions of conjugated dienes, so 1,2, 1,4 reactions. And now we're just doing kind of like a question based off what we did last time so we can kind of refresh our memory. So, what are you all thinking so far? If you have absolutely no idea, that is okay too. But I just want to know, like, what do you remember from last time? What do you think we could be doing? Okay, so someone said they don't even really know how to start this problem, and that's completely okay. So, what we're going to think about here, right, is we know that these two double bonds are exactly the same, right? So it doesn't matter which one we use to attack because the final product will look the same either way. So we know if we do a 1,2, 1,4 reaction, we attack, give those electrons back, and we can either directly form the cation and have Cl minus attack. And I'm so sorry, but I'm going to move this over just a tad because surprise, surprise, I didn't give myself enough room. So if that's the case, we end up with the hydrogen and the chlorine 1 carbon apart. So we get the 1,2 product. Or we could have done resonance, which I'll do in purple, and we could have gotten the hydrogen doesn't move, but the cation moves over here because we moved the double bond. And once the chlorine attacks, we get HCl, our double bond. So now we get the 1,4 product. So it's pretty much exactly the reaction we did last time, but the double bond is just a little bit different. Instead of a ring, it's just linear, right? So we know that the two products we can get is something that looks like this and something that looks like this. And he will give you your answer choices kind of written out this way, so it's a little bit harder to see. And you're just supposed to convert this into the line structure and figure out which one of these two does not match this. And someone asked where I'm getting the numbers from. So basically what we talked about last time was kind of picking arbitrary numbering. And what I mean by that is we're not necessarily doing IUPAC numbering. I personally like to always start where we add the hydrogen. So the hydrogen is always going to be 1. And then we see 2. Versus up here, we start again at the hydrogen, 2, 3, 4. So here their relationship is 1, 2, versus over here the relationship is 1, 4. Does that make a little bit more sense where I got the numbers from? Yes? Okay, sweet. You're very welcome. All right, so now, excuse me. So does A look like either of these? No. So how do we automatically know that this doesn't belong? What's different? Yeah, so the double bond is, the chlorine is directly attached to the double bonded carbon. That's not going to happen here. So this one, for that reason, is wrong because the chlorine is attached to the double bond. Correct. So B, what do we think? Does that one check out? So someone asked a great question. Do we need to draw the bond line formula for each choice or just look at the placement? So a lot of people, like myself, need to draw it out. Like I'm not drawing it out now just to show you guys like the simpler way to do it. But if you need to draw it out, by all means, spend that extra minute and draw it out. But you absolutely don't have to. Like if you can look at this and see, oh, double bond, this is right on the double bond, it doesn't work. Then that's a lot faster. And someone said that this one is going to be the 1,4 product, and I would definitely agree with you. So this checks out. And here, let me not X that there, but I'll say that this is wrong. This one is right. So what about this guy right here? What do we think? Bam! Sorry, I had a coffee today, and so I have a lot of energy, but I'm trying to keep it inside. Come on, people, what do we think about C? Okay, so one person made a really good, like pointed something really good out, but I'm gonna wait one more second to like actually talk about that. But yes, some people were saying that this does check out, and this is where people usually get tripped up. You are correct. This does look right. All they did was take the 1,2 product and flip it around, so now the double bond is on the other side. But you guys are too smart to fall for the trick. Or I won't say too smart, because even if you fell for the trick, you're smart, but you're too good. Your peepers are too good. All right. And then the other thing that someone pointed out, this chlorine is again attached to a double bond. It's essentially the same as A, just flipped around. So this one is not going to happen either. So the question is asking you which is not a possible product. So which ones are we going to pick? A and D. Cool. Perfect. We love to see it. Okay, so any questions, comments, concerns, anything of the sort? Someone said, please help, I don't get it. Okay, I got you. All right. So essentially, if I could hold on to my pen. So let me just open up a new page. All right, so essentially what it was asking is if we have this and we react with HCl, which of the following is not possible? So the answer choices were it was showing us this, I believe, or maybe it was this. I actually have to look because I don't remember off the top of my head which was which, and I don't want to confuse anybody. All right. I believe C was. Nope. I literally have the memory of a chipmunk. No, I was right. No, memory of a chipmunk. I apologize. And okay. And yes, this is pretty much like the hydrohalogenation from chapter 1, or from Orga 1. It's just slightly different because now we have two double bonds. So we know that when we do this reaction, we can either get the 1,2 product, or we can get the 1,4 product. So we're basically looking at these answers and we're seeing which ones match up to these. So A does not look right because the chlorine is on the double bond. Hate it. We don't want that. Ew. Here, we see that it looks just like this product, so this one checks out. Here, we see that it looks just like this product, so it checks out. Here, this looks awful. It's on the double bond. We hate it. So A and D can never happen. And yes, so someone said the hydrogen is always going to be added to the less substituted side. Excuse me. And yes, that's true. That's the most stable configuration. So as far as this class goes, it's going to add to the least substituted side. However, I do want to point out that in this example, both sides are exactly the same, so there won't be really any difference. Cool. Any questions? You guys ask wonderful questions. You're so welcome. I hope it makes more sense now. Alrighty, so are we ready to go into the big bad Diels-Alder reaction? And yes, I can definitely scroll back up. Oh, hold on. I just realized that I actually drew this wrong. Okay, so all the concept that I said still applies, but it was supposed to look like so. I just put the double bond in the wrong place. Ah, someone said it's frozen. Is it back? Can you guys see it now? You're good? Okay, cool. So basically I had just drawn the double bond in the wrong place. So let's look at it now. Now, does it look possible or does it still look ugly? What do you think? Yeah, so now it looks like this product. So it's essentially the same as this. So this is actually going to work out. And the answer is going to be only D. I'm so sorry for that mistake. I hope it wasn't super, super confusing. The concept is exactly the same as what I just explained. The only problem was I drew the double bond in the wrong place. But does it make sense or did I completely lose anyone? One person said I'm good. So someone said it makes sense. Okay, so I'm going to take that as a good sign. I will leave this up for one more second so you can take pictures or whatever. So A was a correct answer, but now we took it off because when the double bond is here, the chlorine is no longer right on the double bond. So this could happen. But if it was the way it was drawn before, it could not happen. So conceptually, what I said still stands. Just be careful where you draw the double bond because you can make a mistake, like moi.
Shouldn't there, on A, the last one be a CH3 then and not a CH2?
Yeah, I think that's why I got confused. I think I just made a mistake when I was making the handout, so let's just fix that. And I will also send an email about that just because I don't want anyone to be like super confused when they do this. Okay. Cool. So I will send you guys an email. I'll redraw everything out and I'll just write a little note on the side in case anyone got confused. All right, so now for real, let's go into the big bad Diels-Alder reaction. And I only say that because it feels kind of terrible, but it's not that bad. So I know it can look super overwhelming, but let's go into it together and try to keep our cool. All right, so the most general reaction is going to be something like so. And what is this thing in the simplest terms? A diene. Swag. I'm sorry. I'm not sorry. I'm gonna keep doing that. Okay. So, we have our diene. And then do you have any idea what the thing a diene reacts with is called? A dienophile. Awesome, awesome, awesome. Okay, so yes, our diene, let's make a note, is going to be any conjugated diene. And we know that a diene is two double bonds with one single bond in the middle. You probably can't even read that, but that's fine. The dienophile is going to be any alkene, which is a double bond, or alkyne, which is a triple bond. Cool. So, between the diene and the dienophile, which one do you think will be the nucleophile? Okay, some people are saying the dienophile, some people are saying the diene, and that's okay. So let's go in here, and I'm going to show you how the mechanism works, and then hopefully that'll clear things up a little bit. So, we have to keep things in track for this, or on, we have to keep track of things, basically, for this reaction. So, I'm going to show you how I like to number everything. So first of all, do you remember back in like elementary school when teachers would tell you we have the less than and greater than signs, and they were like, "Oh, it's like an alligator, right? And like it's going to want to eat the bigger number, so it opens up to the bigger number." I really hope I'm not the only one who knows what I'm talking about, but whatever. So yes, cool. So we're kind of going to think about the diene in that way, right? So we have the greater than sign or less than sign, and we're going to almost pretend like these parts are the double bonds. So it's like this is the chomping side. So this wants to open up its mouth to eat the dienophile. Is anyone completely lost and like has no idea what I'm talking about? Okay, cool. I'll take that as a no. All right. So with that in mind, we're always going to want the diene to be about ready to chomp up this thing, right? And so we're gonna like number the mouth, right? So we're gonna start with the top and we're gonna say this is 1, 2, 3, 4. All right. And then once we go into the dienophile, it doesn't really matter for this class how it's oriented. We're just going to say that the top is A and the bottom is B. Okay, so once we have everything numbered and labeled, we're going to connect 1 with A and we're going to connect 4 with B. And the reason I did like a dotted line and not a regular line is because we haven't made a bond yet. We're just talking about what's attracted to what. All right. So at this point, the double bond from the diene is going to use its electrons to make a bond. So it's donating its electrons to turn this dotted line into a real bond. And so that's going to make this double bond use its electrons to create a bond here. And so that is going to make these electrons move over here. So basically, we have a big circle going on. Is anyone completely lost about how I did these arrows and why it's a circle and where the alligator fits into all this? Someone says, what's it mean though? Okay, we're getting to that, right? Okay, I just wanted to make sure no one was just sitting here like, what in the world is going on? All right, so once we have this, we are forming, we're always going to form a six-membered ring, right? And so in our product, we have one, two, three, four. We have A and B. And I'm going to highlight the new bonds we just made. And so the yellow is the new bonds that we just made. Excuse me. And basically, we just went from two linear things to one ring. And someone said, why did I number or why did I label the numbers? So sometimes he won't give it to you nice and pretty like this. You have to orient it. So I want you to know that you're always going to do the chomping alligator. You're going to start at the top. You're going to go 1, 2, 3, 4. And 1 is always going to connect to A. 4 is always going to connect to B. And that's why I did the numbers. All right, so now that we've seen this reaction a little bit, do you think we could do this if the diene was like facing the other way? So if it was like this, do you think we would be able to do the reaction? No, exactly. So the diene must be in what conformation? Yes, must be an S cis conformation. And we're going to talk about that in a little bit, but you're on to something. The person who said something different than everyone else. You're onto something. We're going to get to it in a second. All right. So for the double or triple bond, we don't really have like a certain conformation it has to start in, but we have to basically maintain whatever configuration we have. So if we start, for example, if we start with trans, we end up with trans. If we start with cis, we end up with cis. And just to make it a little bit more clear, trans double bond will equal a trans product. Cool. All right, so based on what I told you about this reaction and how it goes, now which one do we think is the nucleophile? Let's keep in mind the nucleophile is the one that does the attacking. Someone said none of them? Both? So it is complicated, and technically what I'm telling you is not the complete truth because chemistry is complicated, but for the purposes of this class, the diene is always the nucleophile, and the dienophile is always the electrophile. And I will write that down. Oopsie. The diene is the nucleophile, and the dienophile is the electrophile. And again, that means the nucleophile is the one doing the attacking, and the electrophile is the one being attacked. For this class, that is always true, yes. in all of chemistry, that's not always the case, but for this class, yes. Sweet. So, any questions thus far? Actually, before I open it up to questions, we'll go over one thing. So, we can have substituents in this class. So, the diene and the dienophile can have groups attached to them, like it's shown here. And someone actually made a good point that goes with what I'm saying right now. So when we're talking about substituents are going to help the diene or the dienophile become more reactive. And what we mean by that is the nucleophile wants to become more nucleophilic. The electrophile wants to become more electrophilic. And as someone said, the diene or the nucleophile is going to be electron rich, and the dienophile or the electrophile is going to be electron poor. And no, I haven't written anything, so it's not frozen. But yes, I just wanted to say that out loud before I wrote it down. So the nucleophile is electron rich, and the electrophile is electron poor. And now that we know that, we can kind of figure out what kind of substituents each one of these wants. So we have something called electron donating groups, and we have something called electron withdrawing groups. Just with the names, which one do you think nucleophiles want? So nucleophiles want to have more electron density so they can attack. So do you think they want electron donating or electron withdrawing groups?
Donating so they could accept them.
Yes. Cool. And so in the chat, we kind of have a 50-50, and that's okay because we're just talking about it for the first time. But here we're going to want electron donating groups. And I don't know who it was that just said something. I think it was Paul. But as he said, it's going to give more electrons, which makes it a better nucleophile. So the nucleophile wants to be more negative, and so we want to have the donating groups to give it more electron density, to make it more negative, to make it more likely to attack. And I can go over this again if anyone needs me to, but the electrophile is going to be the complete opposite, so it wants electron withdrawing groups because it pulls away electrons and it helps what in the world? It helps increase electrophilicity, aka more likely to accept electrons. So I'm going to zoom out. You can see both at the same time. And just to reiterate, so the nucleophile is the one doing the attacking. So it wants to have more electron density. It wants to be more negative. So it wants to have electron donating groups so that it can get more electron density, it can become a better nucleophile, and more likely to attack. And I'll actually write that last point down too, aka more likely to attack. That's a terrible K. And electron withdrawing groups have the opposite effect. So they're going to take away electron density. And since our electrophile wants to be electron poor, it wants to be attacked, it wants to be positive, we want to have those electron withdrawing groups to pull away the electrons and make it more likely to be attacked. And someone said, what do I mean by maintaining configuration? So we're going to talk about that in just 1 second. So we're going to put a pin in the question, and if it doesn't make sense in about 2 minutes, ask me again. Okay. So now we're going to talk about electron donating and withdrawing groups a little bit more. And I'm just going to give you kind of a list of different groups. So for electron donating groups, we have, I'm sorry, lone pairs. That's a big one. And so lone pairs are going to increase electron density and donate negative charge. And something that goes along with this is negatively charged groups. For example, I'm going to do the examples in blue. We have NH2. NH2 has a lone pair. And just in case anyone doesn't know, this squiggly basically just means this is where it attaches to your chain. So let's say this is my chain. This is my NH2. If we're only talking about the substituent, we would basically just do a squiggle here to tell you we don't care what the chain is, but this is attaching to the chain. It's just one of those things that they show you a bunch, but they don't really tell you what it means, so that's what I'm here for. All right, so another example here is OH, because it has those electrons. And again, another O group is an OR, and an R group is just any carbon chain. Okay, so these groups are actually going to donate via resonance. Okay, and someone just asked me to say again what the squiggly line is. So all the squiggly line is it's telling us kind of where this group that we're talking about attaches to your chain. So it doesn't matter what the chain is, it's just saying that this is basically the bond that attaches to whatever group you're talking about. So for example, we're talking about dienes, right? And so if we have N squiggle, we know that the N is going to attach to our diene. And since I have this drawn, I'll explain what I mean. So if we have that group, it's going to donate electron density like this via resonance. And so since it pushes that in here, this is more likely to go ahead and use its electron density to go and attack. So that's what I mean by resonance. Any questions about that concept so far? Okay. So next up is we're going to say R groups. So R groups are going to be weakly that looks ugly. Weak donators. And this means that they donate electron density, but not a lot. So they actually are going to donate electrons via electronic effects. And we kind of already talked about this earlier in the semester. And we basically said that if we have the aldehyde versus the ketone, the methyl group over here will donate some electron density. And in the ketone, we have double the donation, right? So it's kind of a similar concept here. So the more methyl or the more carbons you have, the more you're going to donate. So for example, we're going to use that squiggly again. If we have a methyl versus this guy versus this guy, let's call them 1, 2, and 3. Which one do you think is going to donate the most electron density? I don't know why I have the hiccups today. I'm so sorry. Yes, so I agree with y'all. It is 3. So since 3 has the most carbons, it's going to donate the most electron density. So these are all weak donators, but this one would donate more than this one would. I don't know why I have 4 boxes, but that's pretty much all I wanted to say for electron donating groups. Any questions? Okay. So 3 is going to be the most donating. So yes. So I had 2 questions basically, which was just basically to reiterate which one is the most versus least donating, and then what I drew out here. So I basically drew out the electronic effects, and so the electron density is being pushed. That's kind of what I'm trying to show here. And so here, let's say we actually draw out the diene so it kind of gives you a better visual. We have a methyl versus this versus a terbutyl, right? And when we look at it this way, we can see that, I'll draw it in black just to give it some contrast. We have 1 donation. Here we have 2 donations. Here we have 3 donations. So this one is going to donate the most, and this one is going to donate the least. So least donating, most donating. So hopefully that makes it a little bit more clear because it's like more explicitly stated. All right. So let's go over electron withdrawing groups real quick. So the opposite of lone pairs and negative charges is going to be positive charges. So positive charge is pretty much telling you right off the bat withdrawing. And we have, oh, I'll do it in blue just to keep up. Actually, I'll do it in pink just to spice things up. Okay, so if we have NO2, we know that NO2 looks like so, right? And so you might think, hey, Rosemary, that's a negative charge. Yes, but this nitrogen has a positive charge. And if we draw out the diene, we can see the squiggle goes to the nitrogen, right? And so the nitrogen with a positive is what's directly attached to the diene. And I'm going to move this over just because it looks really crowded here. Ta-da. And so since that nitrogen is directly attached, and that's the one with the plus charge, we can say that this group is withdrawing since it's positive. I feel like that was a very wordy explanation. Please just let me know if anyone's confused. Okay, someone said they're lost. That's valid. All right. So but if anyone tries to speak to me and I ignore you, my headphones are just being wonky. But yes, I will re-explain it. And I'll just redraw it and we'll fix it out. Okay, so positive charge basically just means withdrawing, right? And so if we look at NO2, we have the N, the O, and the O, right? And we know that the negative charge is going to bounce back and forth between these two oxygens, but this is always going to be plus, right? And when we draw out our dienophile, I know I drew a diene in the last one, but that might have just confused everyone, so I'm just going to stick with our regular old double bond. And this double bond has the nitrogen attached, and then attached to the nitrogen we have this stuff. The nitrogen is positively charged, which means it wants electron density, right? And we know that these electrons are kind of moving back and forth here, right? So it's getting its electron density from that resonance, but also it's going to want to steal some electron density from the dienophile. So that's what I mean by this positive charge is going to kind of take a little bit from the double bond in addition to the oxygens. And someone asked a great question, which was, could the O minus be considered electron donating, or does the nitrogen's positive override the entire molecule? So we're kind of, both are true. So the oxygen is donating, but it's not donating here. It's strictly going between these three molecules. And since the nitrogen is positive and the nitrogen is what's directly attached, that's going to be the one that overrides the whole thing and defines the whole functional group. Does it make a little bit more sense when it's drawn out this way? Okay. I got a couple yeses, so perfect. I'm going to delete this because it seems that this was just unnecessarily confusing. And I'm going to bring this up here. Bam, delete. Someone said the other one made more sense. Well, that's okay. Whichever way you understood it is absolutely fine. Just remember that the electron withdrawing groups are going to end up on the electrophile, not the diene. All right. So in addition to positive charges, we are going to have halogens. So can anyone tell me what the halogens are? Oh, just kidding. Well, whatever. Usually I just write X and I'm like, does anyone know what this is? But yeah. So the halogens are like fluorine, chlorine, bromine, etc. And it's gonna look That's a terrible squiggly. It's going to look like so. I heard someone unmute. Did you have a question or was that just an accident? Accident? Okay, that's completely fine. Don't apologize. Okay, so we can have either just one halogen directly attached, or we can have something like this, CF3. And so CF3 is super, super, super withdrawing, right? This is 3 fluorines on 1 carbon. That's going to withdraw a lot of electrons. Whereas the halogen itself, just by itself, it's a little bit withdrawing, but it's nothing like insane, you know? The other example, we have the CN group. And does anyone know why this would be withdrawing? Because didn't we say over here that nitrogen is donating? So why is it suddenly withdrawing here? The C is attached, not the nitrogen. Perfect. Okay, that's really good. But there's one more part to that. So you're correct, but there's one more piece. And if you guys don't know, that's completely fine. It does have a lot of electrons because this looks like so. The other nitrogen just had a lone pair, but remember, CN is a triple bond. And then people go, but wait, if it's a triple bond, why doesn't it donate, right? The reason it doesn't donate is because the resonance is going to push that way. So the electrons are going to go towards the nitrogen away from your dienophile. So it'll be something like this, and the electrons will be pushed that away. So we end up pulling electron density from here. Any questions on that one? And technically we are supposed to be done now, but I just want to finish the electron withdrawing group, so I'm going to stay for a couple extra minutes. But I will send the attendance in case you didn't do that yet. Okay, so the last thing we're going to talk about is carbonyls. Pretend there was confetti. All right, so carbonyls are really fun because there's a trick in here. So we have aldehydes, we have ketones, we have carboxylic acids, and all of these are withdrawing because this double bond is going to take electrons up to the oxygen. So we would have resonance up, which would take electron density from here. Yes? All right. And someone asked, will the recording be up on YouTube today? Yes, I will try to upload it today. Sometimes it's really annoying and it takes forever, so latest tomorrow morning, but hopefully tonight. All right, so this is a super withdrawing group, right? Carbonyls are super withdrawing. The last carbonyl we have is the ester, right? This is where we have the trick. Okay, please pay very close attention. So I'm actually going to draw it on the extra page here. So this is an ester, right? We have 2 R groups on either side. So now this can either be attached from the left side or it could be attached from this side. Do you think there's a big difference on which side you attach from? Let's say this is A, this is B. Do you think there's a difference between A and B? Yes. Good. I did say it's a trick, so I guess that was a little bit of a gimme. Someone said maybe. That's fair. That's fair. So someone else said no. Okay, cool. We have a perfect mix of yes, no, and maybe. Awesome. I'm just teasing at this point. All right. So there is a little bit of a difference based on where the squiggle is, right? So again, remind me, what does the squiggle tell us? Yes, so the squiggle means that's where it's being attached, right? And this side is being attached to a carbonyl versus this side is being attached to an oxygen. And so oxygen, yes, it has resonance because of these lone pairs. Awesome. So if the squiggly is on the carbonyl side, aka we attach at the carbonyl, this is going to be an electron withdrawing group. But if we are attached from the oxygen side, so like this, and then this is just more natural to me. Actually, I don't want to confuse anyone. I'll go like that. This side is going to actually be an electron donating group. So there actually is a big difference. I want to mention, before someone asks, yes, the resonance does go this way. However, it can also go that way. So it'll be like this isn't a strong donating group, but it like 50% of the time it could donate into the diene. Sometimes it'll go towards the double bond. So it could go either way. So for that reason, it is a donating group. And yes, so I got two questions about this guy. So the reason this one is not donating again is because it's only going this way. So it's only going here. It's never going to go towards the ring. And since it's a double bond, the electrons are going to push this way. And so there is going to be some push out of the double. Oopsie, I lost my charger. There is going to be some push away from the dienophile. Did that explanation sort of make sense? Esters are kind of a pain sometimes. Makes sense? Perfect. All right, so that is all I have for you right now. We'll go more into Diels-Alder next time. But yeah, please look into it a little bit. We'll do some practice problems. And please don't forget that this Friday is the exam review. It will be recorded. It will be posted. I am going to record it in 3 different pieces, and I'm going to probably I'm going to record it in 3 different pieces, and I'm going to upload it in 3 different pieces. So it starts at 5. So 5 to 6 will be like 1 recording. 6 to 7 will be 1 recording. 7 to 8 will be 1 recording. Hopefully it won't be too confusing. And then someone wanted me to scroll, so yes. Ta-da. And then I can scroll down if anyone needs it. Just let me know when. All right. So I will say goodbye to you all. I will stay for another minute if anyone has questions or wants to take a picture of anything. But I hope you guys have a wonderful day, and I hope to see you later this week. Bye! You're very welcome. And yes, I can scroll down. I assume you want this, but I can go to the middle page too if you need it. You're very welcome. Bye-bye. Bye. You're very welcome. And I'm going to stop the recording. So adios.